Okay, so today's a really exciting lecture though. So we're going to basically follow up on what we were talking about last time, which was reinforcement learning. And in some sense, in the last class, we did some of the hard work in, building up the algorithms, really talking about reinforcement learning in a general setting. And so today we're going to apply them to LLMs. And there's really kind of a lot of interesting details and a lot of interesting variations to go through. And so it really deserves its own lecture. And hopefully you'll have a good sense of kind of two different major ways that reinforcement learning is used in really modern LLMs. Okay, so if you remember last time, we talked about reinforcement learning fundamentals, and we didn't really talk about LLMs, right? Like the example I gave was with this cart pull task. I did kind of motivate things with language models in NLP at the beginning, but we went through this formalism called MDPs. We went through policy gradient methods, and then some improved methods for things like stabilizing training or having better assignment of rewards to different states and actions. Okay, so the way that today's lecture is structured is we're basically going to go through three different case studies. And along the way, we'll see at least kind of two major ways that reinforcement learning is used with language models. And then I'll actually introduce some more techniques that have been developed as we're going through the case studies. Hopefully by the end, you'll also have a good picture of some of the major terminology that gets thrown around when we talk about reinforcement learning for LLMs. So terms like RLVR, RLHF, GRPO, these different acronyms that you'll see. Okay, so really at its core, what we're going to be talking about today is fairly simple. So we have this simple loop where, we have our language model, we generate some outputs with it, then we measure we compute a reward function on those outputs, and then we somehow update the model's parameters with, a variation of policy gradient or the PPO loss that we saw in the previous lecture. But if we actually want to think of this as applying reinforcement learning to language generation or with language models, then we really want to formulate things in the reinforcement learning language. And so the first step, maybe like step zero, is to just frame the problem as an MDP. Okay, and so we briefly actually talked about this in the last lecture, but first I'm actually going to introduce something which is even simpler than what we saw in the last lecture. And you can call it a kind of one-step MDP. So in some sense, it's maybe the most boring MDP or framing of, a reinforcement learning problem that you could think of, but it actually turns out to be pretty useful. And we can frame a variety of kind of use cases with the LLM as this one-step MDP. Okay, so it's basically like it sounds. We have a single step. So we have the state, which is the prompt, and then you have a kind of final state, which is the prompt plus a response. So your action here is going to be just generating a full response. We're not going to break things down into like individual tokens. And what we were calling the policy in the previous lecture is going to be the language model. Okay, so you use the language model to take in this initial state, which is the prompt, to take an action, which is generate the full response. And then your environment transition is going to be, again, kind of simple. It's basically going to be, concatenating this response that you've generated to the prompt. Now, since we only have kind of one state transition, there's really only one opportunity to get a reward, right? And so when you think about it, it's basically saying, okay, we want to run our reward function on the full response that the language model has generated. Okay, so this is framing things as an MDP. And so now we can imagine applying the algorithms that we saw in the previous lecture. Okay, or you can frame things in terms of kind of token by token generation. So we could call this the token level MDP. Here we have the state being the prompt and the tokens that you've generated so far. Your action is generating the next token. Your policy, again, is a language model. And then your environment transition is, again, kind of, boring in some sense. It's appending the token to the previously generated tokens, and that will deterministically get you some next state. Okay, so here is the place where the one difference comes in. Now we can imagine assigning rewards to not just the very final time step, but we could assign rewards to these intermediate time steps. But suppose that we can only get the reward at the final step. Let's say we're solving some math problem and our reward is checking whether the answer at the end is correct or not. Then maybe what we would do is we'd say, okay, the reward for these intermediate steps is 0, and then we have this reward once we get our final output. Okay, so then if you think back though to the previous lecture, then what we talked about is these ways of assigning advantages to individual states in a trajectory, individual states or actions, right? So here, if we frame things in terms of this token level MDP, then we can actually, imagine assigning these more fine-grained advantages. So for example, one thing that we talked about was using discounting, right? So if we get the reward at the very end of the sequence or trajectory, then we can use this kind of discounting to say like decay the reward in time. And then if you really were able to somehow get intermediate rewards for tokens that you're generating, say you can like find out which token really leads to like making a mistake or something like that, then you would use this token level MDP to kind of formalize things. Okay, but then, once you have an MDP, we can imagine, again, applying the algorithms from the last class. And so an example would be policy gradient or some better variation. And again, throughout today's lecture, we'll go through and we'll review exactly what algorithms that we're using. Okay, but again, we can just kind of zoom out. So and kind of take a look at the overall algorithm. And then we can think about which parts will vary in a particular application that you have with a language model. Okay, so the inputs to your kind of reinforcement learning algorithm will be some language model. And then when you think about it, it could either be pre-trained or it could be fine-tuned. Then you have to determine, what are the inputs X? So what are the prompts that you're going to kind of run this RL algorithm with? And then what is your reward function? Then you basically go in this loop. So you generate some outputs with your language model, you compute your rewards, and then you compute some loss function, and then use your optimization algorithm like SGD or Atom as we've been doing throughout the class. Okay, so then here's like a simple loss function that we have right with policy gradient where we have the rewards at each for each state and for each action. And then we have this gradient of the log probability under the model. Okay, so in some sense, you might be asking, should we just end the lecture here? Because I've just introduced how to do reinforcement learning with language models. But we can actually think about these things. You can imagine like, okay, now go off and do this on for an actual application. You would end up still having to figure out a few things. Okay, so first you'd have to decide, should I fine-tune my language model for the task that I'm trying to solve, or should I just use a pre-trained model? Kind of what are the trade-offs, what are the requirements? Then, as I mentioned, you have to figure out kind of what data set of inputs are you running this reinforcement learning on. Let's say you're trying to like, solve math problems, then kind of which set of problems are you running reinforcement learning on? Again, what is your reward function? And then down here is just saying like all of these details that go into actually implementing and running the algorithm, right? So what advantage estimation are you using? Which kind of loss variant are you using? And then just a variety of other hyperparameters. So for instance, let's say you're trying to distribute the training across multiple machines, then you have to figure that out. We actually won't talk about the distributed training in this class, but I'm just saying that, when you actually go to do this, you end up having to figure out things to actually get things to run properly. Okay, so in each one of these case studies we'll go through, we'll look at some examples, and if you kind of zoom out, they'll end up varying along these kind of different axes here. Okay, so now we'll start going through the case studies. Let me just check. There might have been one question in the chat. Okay, so do we assume that we can compute rewards for each generated output? Um, so here in these simple, not simple, in the examples we'll look at today, the last two are in some sense like, state-of-the-art examples. Here we assume that we have some way of computing the reward. Um, and in general, when you have an MDP, you assume that you have this reward function. And so that is kind of part of the picture if you're applying the reinforcement learning algorithm. Okay, so now we can go through to the simple example, which is reversing a string, right? So here the model is going to get the string as input. Our goal is going to be to reverse it, and you can imagine we can check very easily whether the string is reversed or not, or not. Now, you might say like, okay, again, we can implement this with a Python program, but the idea is that, actually, if you look at the code that's implementing this or the ideas that we're using, you could actually imagine applying this to really a wide variety of tasks. And when we talk about the example of solving math problems, which was like a nature paper, it'll actually use a lot of the ideas that I'll introduce for reversing these strings. The other nice thing is that we have an implementation of this, and you can basically run the training on a Colab notebook in under an hour. And so you can do these kind of really fast experiments. You can try out different alternatives and get a lot of insight in this kind of simple, maybe like synthetic um, test bed scenario. Okay, so here, if you remember our four different steps, the first one was, should we fine tune or should we just use a pre-trained model? And so here it's going to end up being beneficial to fine tune first on some data set of input and output. And right here, the output is going to be just the input reversed. So if you remember in the SFT lecture, the supervised fine tuning or fine tuning lecture, we actually looked at this problem of reversing strings. And I don't have like a screenshot or anything here, but if you kind of remember back to that lecture, if we tried just prompting this very small model to reverse the string, it was giving us kind of garbage. It would think that, it would think that you were on some like internet forum and start generating a conversation, or we kind of couldn't get things into the right output format. And so that's actually a really good justification for fine-tuning the model before we do the reinforcement learning. We'll kind of have some guarantee, that the model will at least output things in the correct format. And so we won't waste a lot of compute or waste a lot of time on doing reinforcement learning just to kind of teach the model the format of the task. Okay, but we can think more uh, generally about this. So, given some pre-trained model, it often is beneficial to do this supervised fine-tuning prior to doing reinforcement learning. So, as I mentioned, it can teach the model the format of the task. So again, this can kind of avoid wasting a lot of time where the model just gets zero reward because it's, you know, not doing the task in the proper format, and we can't run the reward function on the output. And then the other reason would be, if you are somehow leveraging supervision from your fine-tuning data set. Okay, let's say we have like a really large fine-tuning data set, then you don't necessarily want to just, throw away all the potential supervision that you can get from the data set. Maybe it actually, for instance, gives you a big boost on a particular task from the point of that you're at from pre-training. In that case, it may be beneficial to, do this supervised fine-tuning prior to reinforcement learning. Um, so if you think about this in terms of reinforcement learning, then what is it saying? Well, it's basically saying that, especially early on, the model just may encounter more high reward examples. And so the reinforcement learning can kind of focus on maybe, harder instances, um, or kind of really maybe like sharpening the model's distribution so that it avoids, particular errors instead of kind of learning the task from scratch. So what are some downsides to fine-tuning before reinforcement learning? Well, first of all, in order to fine-tune, you need a data set, right? And so in general, as we discussed in the fine-tuning lecture, it's not always clear how to get a lot of data, especially if the task is really complex. Okay, so sometimes you might, skip the fine-tuning, or you will really just do the fine-tuning again, so it kind of teaches the model the format of the task. One common thing you might do is you might use, say, a larger model to generate, let's say, like 100 or less than 1,000 examples for your task. It might have some inputs, maybe a chain of thought, and then an output. And again, this isn't so that the model kind of masters the task. It's so that you start the reinforcement learning and you don't make a bunch of like meaningless kind of formatting mistakes. Now, let's suppose that you do have a really large fine-tuning data set. Is there still a potential drawback? Well, again, we talked about this during the fine-tuning lecture. You can think of fine-tuning as, changing the model's output distribution. And so what can happen is if you do kind of too much fine-tuning, then it can bias the model too much. And then the reinforcement learning in some sense is already in a kind of local optimum. Okay, so let's say that you fine-tune a model on a bunch of like human written solutions to math problems, for instance. And it turns out that these human written solutions aren't very good. They like skip a lot of steps, or maybe they even have errors in them, something like that. Then it might be hard for your model to actually learn, brand new strategies that aren't in those human written solutions. Okay, and we actually saw an example of this if you go all the way back to the prompting lecture. There they showed this one interesting experiment showed that the model was actually doing better in a kind of prompting setting if they only gave the model the inputs to the task and maybe a description of the formatting it should use. The model was doing better compared to if they gave the model the solutions as well. Again, potentially because this can kind of bias the model in a particular direction. Okay, so these are kind of the pros and cons, and you might consider these if you are going to do reinforcement learning. Okay, so going back to our simple example, as I mentioned, we'll kind of use these case studies as chances to discuss these more general ideas. So here we do the supervised fine-tuning. Um, Here, I think what we do is we take a data set. I forgot exactly how large the data set is. We fine-tune the model for one epoch, and then we can evaluate how good it is. Okay, so here, this example is from last semester. Here are the names of the course staff from last semester. So I was teaching the course, and then here's the TA names. I guess the model could reverse my name successfully, but it struggled with some of the other TA's names. When we evaluate it on the test set, the model is, far from perfect. It's getting what, about 65% for just reversing these kind of simple strings. So now the goal is going to be, let's use reinforcement learning to, you know, have the model get a lot better. Okay, so here again, if you remember our, you know, desiderata for applying reinforcement learning, the next step is what is your reward function? Here, the reward is pretty simple. So if the output is the reverse of the input, we will give a reward of 1. Otherwise, we'll give a reward of 0. Okay, what is the more general idea here? So it turns out that, again, this example is really simple, but it really is representative of this class of problems that you can apply reinforcement learning to. There's this class of problems, and it goes by the name of verifiable rewards. Or this particular reward you could think of as a rule-based reward. So roughly speaking, what does this mean? It means that you have some reward function, and in some sense, you can really trust the reward function. Okay, like here, maybe we can reasonably trust that if we evaluate whether the string is a reversal of a string, that it's a kind of, trustworthy reward function. In this case, we would say that the task is verifiable, right? We have a good verifier for the task. Um, so what are some other examples of this? Well, when we'll look at solving math problems in a bit, then you could think of some aspects of this math problem solving as being verifiable. So what do I mean by that? Well, let's say we're trying to solve this 2 plus this problem, what is 2 plus 3? And let's say the model might do some chain of thought, it might write a solution, and then it gives us some answer at the end. Okay, well, we can say like, okay, if we assume that our questions end in a single integer answer, like a unique integer, then you could have a verifiable task, right? Because you could check whether the answer that your model produced is equal to the answer for that problem. Okay, and this is actually going to be the kind of trick that people use to, as we'll see in the second example, to train language models for solving certain types of math problems. Now, based on the way I've been describing it, you can probably also see some limitations or some weak points in, having these tasks that you consider to be verifiable. So first of all, like not all math problems or not all scenarios involving math end up having some single answer at the end, right? Let's say we're generating a proof, then that doesn't really have a single answer, and we have to actually like look at the proof to tell whether it's correct or not. Okay, so sometimes it's not always obvious how you create a verifiable reward for your task. The other downside is if you think about this, the solution or even like the reasoning that the model's using in order to get to the answer, then that's not really captured by our reward function, right? The quality of that is not captured by this reward. So if you really care about the correctness of these intermediate steps, then you might have to do something else, or just hope that it's correlated with the answer correctness. The third downside is that you still have to know what the answer is, right? In order to implement this. So these verifiable tasks often do still require some knowledge for the particular problem or the particular problem instance. Okay, and again, if you think about like really difficult math problems, just to keep going with this example, sometimes you actually don't know the answer, even if it is one of these problems that ends in an answer. Okay, so those are some of the pros and cons. And again, the general idea is this verifiable rewards. And so our first acronym is RLVR, reinforcement learning with verifiable rewards. And you'll see this idea come up if you read some of the papers involving LLMs and reinforcement learning. Okay, so what are some other examples? Um, well, you could view, running test cases as some kind of easily checkable property of a program. Okay, so here, this is also showing that it doesn't have to be binary, right? You could have something like the fraction of test cases that are passed. Here, in the case of generating programs and trying to do RL, here you actually have to be a bit careful. So the fact that a program passes a finite set of test cases doesn't necessarily mean that it's a perfect program, right? I mean, you might not have perfect test coverage, for instance, for your program. And so here, people might refer to this as a, verifiable reward, but in some sense, these test cases might not actually be a perfect verifier of whether this program is kind of implementing the original intent of the program. So we'll actually return to this later in the lecture when we talk about what's called reward hacking, where the model learns to get high reward, so it learns to like generate programs that pass the tests, but then you look at the program and it's like not actually what you want the program to do. Okay, so anyways, let's keep going with the simple example here. As I mentioned, we have a code example. Let me actually just show it here when I take these screenshots, it's looking at this code here. So if you haven't seen this before, or even if you have and want to work through a kind of really simple example of reinforcement learning, I'd recommend going through this. Um, so here it has the whole pipeline. It has the SFT stage. This is just from our previous lecture. And then it'll have this RL algorithm, and it's implemented in this notebook that you could run on Colab. Okay, here I was using this A100, and I got this through, at least last semester, there was this EDU account you could get, and then you can get the A100. If you use the free GPU, it'll be a bit slower, but here the whole thing should run in like less than an hour, and it has the whole um, implementation that I'm about to talk through on the next slides. Actually, the implementation is inside this Python file here, reverse PPO. Okay, so what are some key parts um, of this code example? Well, the key part here that we're talking about is the reward function. Here again, the reward is, pretty simple. It's really just implementing this logic of, extracting the string and then giving a one if it's the reverse and a zero otherwise. But the idea is that, if you want to reuse this for some other task, this is the part where, you'd implement your reward function. Okay, so if we frame this as an MDP, we can just use this really simple one-step MDP that I was mentioning, where you have your state, which is the prompt, and then your action will be the full output string. So now we can think about actually using some reinforcement learning algorithm, and we could think about like, okay, which loss will we use? As a spoiler, we'll use the PPO loss from the previous lecture, and what advantages should we use? So here I'll introduce a new idea. And again, this is a really popular idea in the context of language models, and it's called group-based advantages. Okay, so the high-level idea, maybe before I show the details, let me just say it and hand wave a bit. So here the idea that we haven't seen before in the previous lecture is we are going to somehow come up with advantages, and it's based on generating multiple outputs at once. And then basically like comparing the outputs, seeing, which of these outputs got a higher reward, which one got a lower reward relative to the other outputs. And then the idea is, you want to push up or assign high reward to the things that got relatively high reward and push down the other ones. So let's take a look at this. So again, for each input, we're going to generate k different outputs. And then here's just giving some notation to those, right? Y1 through YK. And then what we're going to do is come up with these advantages. And again, this advantage is going to be for the whole sequence. because we have this really simple one-step MDP. So what do? Well, we take the mean reward from these K outputs. We'll call the K outputs the group. And then we can optionally normalize. So for instance, you can use the standard deviation of the rewards in the group. Okay, so let's walk through an example. Here, our group size is going to be 4. We generate 4 outputs. Let's say that 3 of them are kind of, not good reversals of the string. I guess they dropped the letter E, and then this one at the end is correct. So our rewards would be like this, 0, 0, 0, 1. And then if we take the mean and subtract, we would get these values here, right? Because the mean is 1 over 4, so 0.25. Okay, so you could see it has the effect of what I was saying before. It's going to assign a high reward to this correct one and lower rewards to the incorrect one. Now we can think about, what are some other effects that this group-based advantages could have? Oh, maybe before that, and then you can also do the normalization by the standard deviation. So what are some other effects this could have? Well, let's say that instead we got 0, 0, 1, 1, then our mean would be what, 0.5, and so our positive rewards would be a bit lower. Okay, and so what's one way of interpreting that? In some sense, this example here, where the model only gets a single positive reward, it's maybe a harder example. The positive reward is more rare. And so in that case, the model is getting a kind of bigger update. If the example is easier, then this mean is going to kind of push down the magnitude of the update. And so it can have this kind of, yeah, maybe like difficulty aware effect, if you want to call it that. Okay, you also have to look out for these edge cases. So you could say, what if all the rewards are 1 or all the rewards are 0? Well, especially, if you're normalizing the advantages and the rewards are 0, then you definitely have to take care of the divide by 0. You might do that by having some, small epsilon, or it's popular to just drop those instances. Drop the instances that have either all 1s or all 0s. Again, this is kind of getting into the details, but if you do look at some more recent papers, related to these algorithms that are being used, people will play around with things like exactly how you normalize the rewards. So some people have found, some people have even tried dropping the normalization Z. Or another argument is that you can use the standard deviation from the entire batch. So not just from the group, but from the entire batch. The argument is that if you have a really large batch, then this is in some sense the population standard deviation. Okay, so you'll see these different tweaks. Surprisingly, sometimes if you make like a single tweak to the algorithm, people will invent a new acronym and say, this is a brand new algorithm. But hopefully through this lecture, you'll get a good sense for, just ways that these algorithms can vary, and then just think about things in terms of, what's varying in the algorithm versus what acronym is being used. Okay, so I didn't go back and like review the idea of advantages because we went over in the last lecture. But if you remember, this is like the way of assigning kind of what weight or what reward in some sense is being used at each state or for each action. And if you remember in the last lecture, we talked about learning this value function. Okay, and the value function basically took in the current state and it predicted what is the eventual return from this state. Okay, and so really a big pro of using this group-based advantage is if you notice, there's no additional learned value function, right? And so let's say you have like a really large language model and a really complicated task, then it turns out that like it might actually require a lot of parameters, or it might be pretty difficult to learn a value function. So instead, these group-based advantages just give you this kind of, simple intuitive idea based on generating multiple outputs and kind of comparing them. So what are some cons? Well, here we're in this really simple kind of one-step MDP, and it becomes less clear how we assign advantages to intermediate steps or intermediate states. Right, so imagine we have our kind of token level MDP. Then the question is, how do you get a group-based advantage for each individual token? You could say, oh, well, maybe I'll do some kind of rollout, like generate multiple times from each token or from each state. Well, then that would actually get pretty expensive. And so that would be the benefit of having a value function, namely that from each state, you can run your value function and then get some advantage for each token potentially or each state. Okay, so these are going to be the kind of trade-offs. It turns out that for a lot of problems, you can get away with, not learning this value function and just using these group-based advantages. Okay, so then here's the code example. Again, there's nothing kind of deep going on in this code. Maybe if you look at it quick, this is just one implementation too. It's not guaranteed to be the best one, but it's just implementing the idea that we were looking at before. Okay, here we're getting the means for each prompt and then subtracting them. And then again, afterwards, you can do the normalization. Okay, so the last thing, and then I'll pause for questions. It's maybe been a while since I paused for questions, but let me just talk about the loss. So this is mostly a review from last class, or it really is a review from last class. So if you remember, we talked about the policy gradient. Here was a kind of general form where you have advantages, and then this is again looking at this like per token MDP. If you were to have the one-step MDP, then you wouldn't have this like time index here. And then if you remember, I introduced this PPO loss, proximal policy optimization loss, and we talked through this in the last lecture. And so here, the one difference again is you have this separate copy of the model, right? We have this P theta old. And then we came up with this ratio, and this in some sense is then scaled by the advantage. And then the other new idea here is you have this clipping. And this ensures that, an update isn't made too far in either direction. Okay, but we do have to think about this p theta old now if we're using large language models. Let's say that your model has, billions of parameters, then you really do have to keep around this separate copy as you're doing these updates on, within the training loop. Okay, and so if you imagine with really large models, you actually have to think about how you manage this, which GPUs you put it on, things like that. In this code example, it's not too complicated, but you do have to, implement saving this additional copy as you're doing the updates. Okay, so we do have an implementation of this loss function. So here is the PPO clipping objective, and it's basically implementing what I showed you on the previous slide. Here it's using log probabilities, so we have this exponential to compute the ratio. And then you can notice that with this clipping, there's two different numbers. So here I actually put this in for a reason. So this has been another thing, when people are kind of playing around with this algorithm, finding different variations. Another thing people try is having a different clipping threshold for basically the positive update direction. Okay, so you can imagine like at least intuitively, maybe if the model makes a positive update, then maybe you actually do want it to make a large update in that case, and so you would set your clipping ratio higher, um, and then the opposite argument for making an update in the negative direction. So this is just another thing where, people will try these different settings, and for some problems, this is the setting that people will use, and it'll get incorporated into a kind of variation on the standard PPO loss. Okay, if you look through the code, you can also see where this copy is being done. And then I think it'll do, a few updates. So it'll say do like 3 updates. And then you would then, move to the next batch of data and then make the copy again. Okay, the exact policy for doing the copying within the PPO loop is again going to be a kind of design decision. And in a really larger scale setting, you again have to be more careful because this making the extra copy might be pretty expensive. Okay, so now we can put this all together and have this loop. And again, I'm not going to go through every line of the code in detail, but you really can see the different steps here implemented, and it really is worth going through because if you look at a kind of like really scalable or something implementation, it might look a lot more complicated, but really at its core, the different RL implementations will have these different steps in them. Okay, so let me see if there's any questions in the chat here before I go back into presentation modes. Um, so what are key signs that SFT is enough and we should transition to RL? So yeah, this will be something which might, vary on a case-by-case basis. Again, sometimes just the amount of data that you'll have will limit you, and that'll kind of make the decision for you. Otherwise, sometimes you have to run experiments. So you might run, a small RL run at different checks checkpoints of the SFT training. And if you do notice um, if you do notice some differences, then that's one way of making the decision. And again, the idea is that, you know, generally the SFT will be a good idea, but you can get into the setting where you do like too much SFT and then it biases the RL training. Then there's another good example of like how do we extract the answer from how do we extract the answer? So um, in general, yeah, this is like, something which sounds boring, but you really have to think about. So one option is you really enforce like a certain output format with for your task. In that sense, or sorry, if you do that, then it can be kind of constraining, and you get a model which can only output in certain formats. So again, something more general would be you use a language model itself to like extract the answer. And generally, if you have a pretty good language model, you again should do some tests to make sure that this is the case. But hopefully you could just rely on that to like reliably extract the answer and make it a bit more flexible. So then if you do end up running this, then you'll see something like this. And again, if you haven't seen, a reinforcement learning run before, then it's really good to have a lot of different monitoring. So here it's using this monitoring framework or this kind of dashboard framework called WANDB, and then it will log a variety of things. So one of the main things that you'll log, one of the main things that you'll kind of stare at or get stressed if it crashes is the average reward, right? Because ultimately this is what you're supposed to be optimizing. In this case, we can see that, it's really kind of nice optimization. The reinforcement learning is, working and the model is getting better. Then we do want to still evaluate the model on some held out data because, again, this is the reward on the training set. So here are our kind of held out manual examples. Now we can reverse the names of the previous class's course staff. And it's still not perfect, but it's doing a lot better. So on this test set, the model is now getting, what, 92.6%. Okay, so that's the simple example with um, reversing the string. And so again, we can look at some terminology based on what we've looked at so far. So sometimes you'll see the term cold start referring to this initial supervised fine-tuning. Um, you will also see, as I mentioned, RLVR for reinforcement learning with verified rewards, the group-based advantage, and the PPO loss, as well as some other kind of specific decisions. That'll be called GRPO. Um, so again, this refers to using this PPO style loss, using the group-based advantages, and then if you really want to get specific to like the original GRPO algorithm, which will be in the paper that we'll look at in the second case study, then there'll be some additional details. Like they are doing this normalization based on the group standard deviation, and they have this additional loss function term, which is the KL divergence. And we'll actually talk about that later when we talk about in the third example. Okay, but you'll definitely see this term GRPO um, come up if you look into, you know, papers involving language models and reinforcement learning. Okay, so now we can move on to solving math problems. And really, not too much is going to change here compared to reversing the string. So what I want to do here is like look at this really kind of like real world, if you want an example. Real world in the sense that this paper got into Nature, really kind of prestigious venue. It had thousands of citations within like months of being released. And so this really was a kind of, breakthrough for the field. So this is a paper called DeepSeek R1, and it focused kind of the main thing, or the main thing it got maybe famous for, was solving these math problems, was the problem setting. And the difference here is that now they were having the model not just output solutions, but have it output some chain of thought prior to writing a solution. Okay, and so the really interesting thing here, and the reason maybe this got famous, is that they saw some pretty interesting phenomena where, due to the reinforcement learning, the model was actually learning to kind of use this chain of thought in interesting ways, and in turn, getting better performance on the problems. So let's take a look at some maybe like specific things that they do, and this will give you some insight into, yeah, an application of the ideas we've seen so far. Okay, so here, what they have is the input is a problem statement, and then here's the actual prompt that they're using. So again, they say it's, some kind of conversation, and here, as I mentioned, they're going to ask the model to output some chain of thought or some reasoning and put it inside of these think tags. Then they're going to have the model output an answer in the answer tags. And then this answer will be what is like parsed and what the reward is computed on. Okay, so here's another area where you can add in some flexibility. Maybe you could have a really strict format for your answer in the answer tags, and then like before the answer tags, you could have maybe like a more flexible um, output. Um, so, so this is really it, and I think this is the actual prompt they're using. So really minimal prompt. And then the output again is going to be a chain of thought and then some answer. So here again, this paper, very famous, big breakthrough, but it really is using the ideas that I just introduced for reversing the string. Um, I guess when I say using the ideas, this was the one that, you know, uh, gave the new GRPO algorithm and showed that this really worked. Um, but anyway, so here they have this one-step MDP. They have two different settings. So they have one setting where they start off with just a pre-trained language model. So the interesting thing is that like without some initial fine-tuning, the model is going to be able to, learn how to use this chain of thought and get good problem-solving performance. They also do have a separate setting where they do some initial fine-tuning, and they have kind of two separate models. The reward is again really simple. They're just checking whether the answer at the end is correct or not. They also check whether the format is correct, and they found that this is, useful. So again, the algorithm that they use is going to be GRPO. So PPO with these group-based advantages, and then we'll introduce this KO penalty that they use a bit later. So they did get into nature. So for nature, you usually have to have some kind of like a, detailed description of what you did. So they have this really long supplementary materials, and you can read through and get some insight into specific things. So one thing you can look at is like the exact data that they used. So you can see for math, they used 26,000 different prompts. And then later in the paper, so maybe like separately from what I'll talk about here, they try to get the model to work on other tasks. So like code, STEM tasks, and even like general tasks. So we'll talk about these general tasks in the third case study. Okay, and then here's just some details if you're curious to go read about the data that they're using for the math problems. Okay, and so here was maybe like one of their key, you know, plots from the paper. So in the x-axis, we have the steps of reinforcement learning. And on the y-axis, we have accuracy on this benchmark, which was, at the time, a very challenging benchmark. It has problems from this math competition, AIME, AIME. Of course, now this benchmark has been like saturated. People have moved to more difficult benchmarks and problems. But at the time, this was kind of very non-trivial, very, very surprising. You could see that over the course of training, the model is just getting better and better. So here, in some sense, the reinforcement learning is, really working. Why is there two different lines? We'll return to this in the very last lecture of the class. This is just using two different inference strategies. So the red line is saying, we're going to generate, at test time, we're going to generate 16 outputs and then take the answer that kind of occurs the most often. So then the really interesting phenomena here is with the chain of thought. So what they observed here is that the length of the chain of thought was actually growing as the model was training. And then interestingly, if you actually look at the contents of the chain of thought, they were finding some kind of interesting patterns. Okay, of course, these are just like tokens produced by a language model, but you could at least look at them and maybe see what the model's generating. So one thing they noticed is that the model was learning these kind of different strategies. In particular, it was learning, as it was generating a solution to say, oh, wait, maybe what I'm doing so far is wrong. Let me reevaluate what I'm doing and take a different strategy. Or, after trying many alternative strategies, it says, wait, oh, I have some key insight. Now I know how to, finish the problem. And so again, the interesting thing was that like, using this reinforcement learning signal, the model is in some sense learning to kind of use this chain of thought productively in order to maximize the reward. And it's learning to kind of use it in maybe like non-trivial ways. Okay, so that's all I have on this. So if you do go and read the paper, there's a lot of other different variations, right? So they have a version where they do some supervised fine-tuning. They have a version where they try to make the model work well in more general tasks. For that, they'll still actually incorporate some of these ideas that I'll talk about in the next example, where you learn a reward model. Um, and then, as I mentioned, this really kind of, you know, led to a bunch of follow-up work. So I think, um, I don't remember the exact number of citations, but you can go look. It's probably like 10,000 citations or something for this paper, and it's been published for like a year or something like that. So we'll actually talk a bit more about this, I think, in the very last lecture of the course, but this is definitely something to be aware of, and maybe what you would refer to as kind of emerging from this research finding is what are called reasoning models. So a reasoning model will kind of produce this chain of thought prior to producing an output. And again, the chain of thought is not just, here is the step-by-step solution. It's actually some kind of the model might be like trying alternatives or backtracking, things like that. Okay, let me pause briefly for questions. So if the sampling in GRPO is poor, resulting in very low variance and a significant advantage, what strategy should we adopt? Yeah, so that's a good question. So there's the extreme cases that I talked about where it's, all ones or all zeros. It's popular to just drop the examples, the training example in those cases. Um, Otherwise, two different things I can think of. One is that you do have this clipping term in the PPO loss, and so that will help prevent these kind of really large updates. And again, people have found that, in some settings, it might be good to like set the clip higher for like a positive update. Um, Then another thing is maybe more general. You could think about like, okay, you can look at the problems or the prompts that you're doing RL on. And you could look at some statistics and say like, are all of these prompts too easy for the model or are they all too hard? Okay, so if your model is getting, mostly all correct or mostly all incorrect, then you can you can change the prompts, to use a different strategy. So you might, for instance, prioritize examples that are of like medium difficulty, or you might do a kind of curriculum learning strategy where you gradually introduce harder examples during training. So that maybe wasn't like your exact question, but it's maybe something related. Okay, so there's a kind of question about like there's no supervision on the chain of thought, and so is it kind of collapsing onto internet examples, um, where math problems might tend to have some solution that have some examples in them, some examples of like backtracking things like that in them. So I think one way to think about this is you can do supervised fine-tuning prior to doing the reinforcement learning. And your supervised fine-tuning could even have, explicit demonstrations of doing something like backtracking or considering different alternatives. And so the one thing, if you want to believe that like the reinforcement learning is actually doing something, then it really is kind of learning to use these patterns that the model knows about in a productive way, like in order to maximize the reward. And so it is possible that the model has seen these different ideas about like backtracking or something like that on the internet. But at the end of the day, if all you care about is reward, then it is saying that like the model is learning to like choose these particular strategies and it actually leads to a higher reward at the end. So maybe that kind of gets at your question. Another thing is that like the model doesn't have to just use these strategies. It can actually like use the tokens however it wants. And you do see some of some evidence um, for this. So maybe let me give an example. So one thing they observed in the DeepSeek paper is that the model would actually just switch languages. So I think it was trained on like both Chinese data as well as English data. And so its chain of thought would just like alternate sometimes between languages. And in some sense, if all you care about is reward, then I don't know, maybe that's actually the optimal strategy for the model. So they actually added a separate reward to, ensure that the model outputs only in a single language. And that's maybe one argument for, the model is just learning to use the chain of thought however it wants to maximize the reward. Okay, so let me keep going just to make sure we might end up having to kind of accelerate through this section, but yeah, hopefully I have enough time. So in this third part, we're going to actually look at, a separate setting where let's say you have like a chat model. And now we're not just trying to solve problems, we're just trying to say, okay, we want to generate some chat completions that are good according to human users. And so the key difficulty here is going to be how do you evaluate the reward? How do you say, whether one output is good or bad according to a human user? So here what we're going to have to do is we're going to have to actually learn some reward function. So a brief intro to, thinking about learning a reward function. So maybe two broad categories to think about. One is you could think about essentially learning a classifier. Okay, here you could call this a direct assessment model, where the model directly outputs it's not necessarily a classification, it directly outputs some score for something that you care about. Okay, so, an example is like, let's say you have some notion of like helpful versus not helpful. Then you learn a model that essentially classifies something as one helpful, zero not helpful. Same with like safe or not safe. And so you can go on Hugging Face and you can find different data sets for, training models in this way. Here's one from, I think, NVIDIA, and they basically collected, tons of data to train one of these safety classifiers. So they got different labels for whether this response was safe or unsafe. Again, how you define safe would be a whole nother topic to go into. It can be very nuanced, but nevertheless, they released this data set, and then you could imagine training a model, on this data set, and then potentially using that as your reward model. But if you think about it, then like, you know, it's still difficult for like a really open-ended task to even pin down like a specific criteria or a specific score for an output. And so another thing people have done is said like, okay, if I'm going to annotate data, it might actually be easier to annotate kind of preferences. So here it's saying that, like presented with an output from a language model, if you have to say, what is the score of this output? Like, is this a good response? Is it a bad response? Is it a 4 out of 5 or a 2 out of 5? Sometimes that's difficult. But if I give you two different responses, sometimes it's easier to say, oh, well, this one's better than this other one, and not exactly say why. So that would be an example of a preference rating. And so now the goal is going to be to train this reward model to basically assign scores such that things that are preferred more often are scored more highly. So how do we do that? And we'll get back to that in a second. But the idea is that, okay, if you have such a reward model, then there's this new acronym or kind of new standard pipeline for reinforcement learning and language models. And it's called RLHF, or RL from human feedback. Okay, so here the pipeline would be you do some supervised fine-tuning so that you have, some chat model or some instruction following model. Then you do this step where you actually have to learn or train this reward model. Okay, so we'll talk about this in detail in a bit, but here you collect this data set of these preference ratings. So it'll be a prompt, it'll be two responses paired together, and one response will be labeled as being better than the other response. Then once we've trained that reward model, you do reinforcement learning to optimize the reward. Okay, when you do this, you're going to actually run into some issues. So we'll return to that later. We'll run into this issue of reward hacking, where the model will basically learn to, exploit flaws in this reward model. It's a kind of learned model after all, and the RL algorithms are pretty clever. And so what we're going to have to do is actually add in some modifications to the loss that we use. Okay, but let's go kind of one step at a time. Oh, and so here's the kind of famous paper that really made this into a big research area, arguably. It was from OpenAI. And here's the kind of key diagram from the paper. Again, it's kind of what I said, and we're about to go through it in detail, so I won't step through this diagram. Okay, so the first step is supervised fine-tuning. Nothing too surprising here. Again, you want to collect this data. Again, here we're in this kind of open-ended setting where you have like a chat model or instruction following model. So if you think back to our fine-tuning lecture, we actually talked about a lot of techniques for coming up with these data sets. Okay, again, they might be pretty general. You have some instruction, and then you have some output. So one maybe like concrete example, just to give you a sense of scale. Again, this will be an open example, so probably what they're doing in the like frontier labs will be even more scaled up or even more nuanced than this. But here's an example where this SFT stage has a data set of 900,000 prompts. So they try to come up with as many kind of prompts as they can. They try to collect their own. You could see that it covers, math, but then it also covers basically anything that they envision the language model being used for. Okay, and so then we do fine tuning on this, and then we want to say kind of how do we improve the model further. Uh, it turns out that like you can do separate types of RL. You can do RL if you have the verifiable rewards, but let's think about like just in general, if we want to, output responses that are more preferable to humans. So for that, we'll do this reward model stage. And we'll try to collect this preference data that I mentioned before. So it'll be an input and then two outputs paired together. And so to do this in practice, you have to make some decisions like, which prompts do you use? You could reuse some from your SFT data set, or you can like introduce some new ones. So maybe I won't go too much into the details here, but there's different design decisions, if you're trying to actually do this. And then you have to decide, oh, and then your responses will be usually from your model from the SFT stage. Okay, so the idea is we're going to try to kind of like adjust the model so that it's more aligned with the human preferences. So now you have to decide how you get these preference ratings and then how you actually train the reward model. So to get the preference ratings, again, you need some decision of like, whether which response is better than the other one. So one thing you can do is if you have money, you can hire human labelers. So, if you're OpenAI or Meta, then you might have like human annotators annotate their preferences. Or you could come up with ways of automatically getting these preferences. So like, on the ChatGPT interface, sometimes it says, which response do you prefer, A or B? I don't know what they're doing at OpenAI, but maybe they can use that as kind of preference data. One thing that's been done in the kind of open source community is to use a really strong model to actually annotate the preferences. So again, you might run into difficulties if you're like trying to train maybe like the very best model. But usually, especially in the open source community, you'll have access, say through an API, to like a really, really strong model. And you could basically use that to kind of rate the responses from your smaller model that you're trying to improve. So here's again an actual example which was used in this AI2 model. And you can see here in the middle box is maybe the thing I'm trying to highlight here. Sorry, the right-hand box. What they do is they took the best GPT at the time, and then they're having it basically come up with these preference annotations. Okay, so now we want to think about how you train this reward model. And when you think about it, we have this preference data. And so we haven't gone over, this isn't just a normal classification task. So we actually have to think about like what loss function do you use if you want to train this reward model. So here's the loss that you end up using, and we'll go through the justification for it, and it's kind of interesting justification. But first we can just look at this, and what it has is it has the reward model score for the positive output. And again, of course, the reward model will also take in the input X. I'm just kind of, reducing clutter by not showing X also. And it has the reward model score for the negative thing. And then if you kind of go through the cases and, look at the signs, it'll basically have the effect of training the model to assign a higher score, kind of like pushing up the score of the positive thing and pushing down the score of the negative response. So it's kind of intuitive, but then we could say, what's the justification for this? So there's this idea of there's this like classic probabilistic model called Bradley-Terry model, and it's a model for the outcome of these pairwise comparisons. Okay, so it's a really simple model, and it says, okay, given two items, we will assume that the probability of this preference rating I is greater than J being true is of this form, and this is basically the simple fraction. So what we could do is we could take this Bradley-Terry model and we could parameterize these probabilities using a neural network. Okay, so this will be our reward model that we're using. And we could say, okay, this PI is going to be, something which is a function of the score that the reward model is giving us as output, and then same for PJ. And now we get this fraction here. Okay, and then you can do some simplification. So you could like divide by this exponent term. You can get this. And then I'm going through this kind of quickly, but you could notice that this is basically the form of this sigmoid function. And so then you arrive at essentially what we were looking at on the previous slide. Okay, so you could see that this loss function or this kind of sigmoid with these two different terms corresponds to modeling this, using this Bradley-Terry model, and the probabilities are going to be parameterized by our learned reward model. Okay, so now that we have a probabilistic model, you could use our other tool that we've, from the toolbox that we've been developing in this course, which is maximizing the likelihood. Okay, so you could say, what if I maximize the likelihood under this model, given our data, then you could have this likelihood function, and then as you remember, we minimize the log likelihood. So now you really arrive at exactly what was on the previous slide. Okay, so that's kind of quickly the justification for this loss. And if you do go look at different papers that are training these types of reward models, you'll often see this loss. I think unless you look at maybe the earlier ones, you often don't see the justification for it. So hopefully it's interesting and it's a kind of good thing to know about. Okay, just in the name of time, I'll keep kind of going. So now we do reinforcement learning. Given this reward function, again, you choose which prompts you're going to use. And are we done? The one issue that you run into is reward hacking. Okay, so what happens is, let's say that your reward model is not perfect. Then again, this reinforcement learning algorithm can be very clever, and the model can learn these kind of ways to exploit the reward function. That means that the reward model gives a high score to the output, but then when you as a human look at the output, it's kind of not what you intended. If you could think about like how this is possible, well, let's say we're in a simple setting where we want to do like, is the output safe or not safe? Um, then, one edge case for that is the model could just output an empty output. And maybe our reward model says, oh, well, an empty sequence is, definitely safe. And then your reinforcement learning, once it discovers that, it'll basically collapse your model onto just outputting the empty string. That's an example. And then sometimes the reward hacks will be more nuanced. Okay, so this is just exactly what I said. So you can actually go in the DeepSeek R1 paper, and they found that this reward hacking actually happens for RL with test cases. Here we're generating programs. And so what happens is the model finds some way to like pass the test cases that are in the training examples. But then if you like look at the programs that are being generated, or if you evaluate the model on a held out set of programs, you can actually see that the performance is dropping and kind of plummets at some point. So that's a kind of classic sign or, symptom of reward hacking. You'll see a mismatch between the reward that's being optimized and then some kind of held out measure of performance. Okay, so we have like 1 minute left, but this is the last thing I want to introduce. What you can do to mitigate this is to basically add in this constraint. And the constraint will basically is a KL divergence constraint. So it will be a regularization which causes your model to stay close to the model that you have at the beginning of reinforcement learning training. Okay, so when you think about it, if your model is kind of reasonable, doesn't output like empty sequences or like weird programs, maybe this constraint can help kind of limit the distance that the reinforcement learning can go. So one common way this is done is through this reward function. And if you go through this derivation on this slide, you can kind of justify this and show that it corresponds to a KL divergence between the model that you have at the beginning of training and the one that you have at the end of training. Um, so I think we're basically out of time, but these are all the kind of major parts for this reinforcement learning with human preferences. Oops, sorry. Again, here the key idea is we're going to learn some reward function, and then it's very common to use this KL divergence constraint. And one argument for it is that it might help mitigate some of this reward hacking. So just one more thing that I want to quickly put up is a way of thinking about all these different algorithms that we've talked about. You could think of them as, varying based on the loss you're using, the reward, and then the advantages. So GRPO will typically, or the original version is this PPO loss with a KL penalty. You can use any reward, and then your advantages are based on this group-based optimization, group-based advantages. PPO in its like most general form would really just refer to using this PPO loss. Typically, when you see it like referred to in different papers, or here it's like specifically in this RLHF setting, then that would refer to for RLHF using this model-based reward, using the KL based penalty, and typically using this generalized advantage estimation, which we introduced in the previous class. Okay, I apologize for going 1 minute over, but we managed to get everything into the lecture. And so hopefully it was interesting. Hopefully you have a good starting point for using reinforcement learning with LLMs.